SwayamPrabha. Digital India. Educated India.
Hello and welcome to lecture 63. So in last lecture we started discussing the design of wind tunnel fan. That's what will be developed at IIT Kharagpur, sponsored by RDSO. That's what is called Central for Railway Research at IIT Kharagpur. We are having the details. This all details, that's what is available with us in terms of test section, maximum diameter of say fan, that's what is required. We also have some constraint with the motor rating, that's what is available with us. So if we look at here, this is what we have started discussing about, and here in this case we have unknown parameters like mass flow rate. We have constraint with the diameter of the casing. We are not knowing what is the diameter of our hub. We are not knowing what exactly will be the axial velocity and other parameters. So we have started discussing about the selection of different parameters, and we have correlated that with say hub to tip radius ratio. So we have correlated our radius ratio with hub to tip ratio and different axial velocity numbers. At the same time we are having constraint with the rotational speed, and that's what we have kept as a 500 RPM. Now based on this parametric study we have come up with say radius ratio of 0.6, and that's what is giving us axial velocity in the range of 43.75 meter per second, and this rotational speed, that's what was coming say 475. Based on that we have made assumption of axial velocity to be 44 meter per second, and we have come up with our rotational speed of 480 RPM. And that's what we have decided as our final parameter for doing further calculation. And in sense of doing the calculation, we have done our calculation at the mean line based on our fundamental understanding, the design approach for industrial fan, for say industrial compressor, or say axial compressor for aero engines. That's what is remains same, it is common. Here in this case this fan is subsonic fan. That's the reason we are doing our mean line calculation at 50% span. Now this is what all we have discussed about. We have assumed our aspect ratio of the rotor blade as say 1.78. We have assumed our solidity as 0.54, and based on that we have started doing the calculation. We have done our calculation at the hub station as well as tip station, because we have adopted our approach of free vortex design. Now based on this free vortex design methodology we have come up with these numbers. So if you look at these numbers, say my diffusion factor at the hub, it is coming 0.41, and diffusion factor at the tip, that's what is coming 0.24. Now here if you look at this fan, what we are planning to design for wind tunnel application, that's what is expected to generate certain pressure rise. Now we are not going aggressively in sense of doing design for such kind of fans. Like in the case of compressor, we are expecting our diffusion factor to be in a large number, say 0.5, 0.55, 0.6. That's what is our expected number. Since this is what is a fan, we are not expecting such high diffusion factor near the hub region. At the same time near tip also this is what is coming slightly on the higher side. Now if we look at our height of the blade, that's what is coming 0.8 meter, and for that 0.8 meter height and chord of 450 mm, if we consider the weight of single blade, that's what will be coming slightly on a higher side. So conventionally what people they are doing, say this is what will be acting like a cantilever. And in order to avoid the structural problem, in order to provide the structural rigidity, people, they are adopting different kind of concepts. At the same time, when we are talking about the wind tunnel fans, these wind tunnel fans, they are having provision for changing of pitch angle. That's what is basically maintaining the mass flow rate through this fan. And at the same time, it is used to manage the flow velocity. That's what is required at the test section. And in order to have such kind of mechanism, in order to tilt the blade at certain angle, we need to have pitching mechanism. So my hub or my station of hub for the blade, that need to be rigid or that need to be strong. So in order to address all these aspects, we have done certain modifications in the design. Let's see what modifications we have done. So here in this case, like in order to address the issue with the structure, with the requirements, special requirements and weight, the chord of the blade, that's what need to be varied from hub to tip. So there are different methodology, there are different guidelines, that's what is available in different handbooks. Especially for the fans, what they say, the chord of the tip should not exceed the hub chord by more than 20% because of centrifugal loading action. Second aspect, it says the chord of the tip should not be less than 2/3 of the hub value of, in order to assume, say in order to have reasonable size of the aerofoil as well as thickness to chord ratio variation for that aerofoil. Now here if we look at, this is what is a special kind of fan, that's what we are using for industrial purpose, that's what we are using for wind tunnel fan. So we are adopting second approach in which we will be having chord, that's what will be different at hub, my chord at the mid section will be different and chord at the tip section will be different. So we need to assume systematic distribution of the thickness, or we can say we need to assume systematic distribution of chord from hub to tip. So in order to address this issue, what we need to do is, here we have modified our chord. So my chord at the hub, that's what we have kept as say 450 mm, and near the tip we have assumed our chord to be 80% chord of hub, and that's what is giving my chord at the tip as 0.36. Now here if you look at, this is what is representing the variation of my chord, say 450 mm, that's what is at the hub, 405 mm, that's what is at the mid station, and at the tip that's what is coming 360 mm. Now when we are modifying our chord, what is happening, our diffusion factor, that's what is going to change. So here if we look at my diffusion factor, that's what is coming 0.41, and at the same time near the tip that's what is coming 0.27. So basically in order to address the issue because of weight, what we have done, we have modified our chord, but at the same time that's what is creating trouble in sense of aerodynamic loading, and that's the reason why we need to address now this particular issue. So what is happening, let's see. Say here if we look at, say this red color one, that's what is representing when I am having constant chord. So this is what is representing how my diffusion factor, that's what is varying from hub to tip. So here in this case, this is what is representing my diffusion factor variation when I am having constant chord. Now when we have modified our chord, under that condition if we look at near the